Now let's talk about autoencoders. So the thing is that before 2011, unsupervised pre-training was required to train deep networks. So what we know is that random initialization of deep networks generate a wide variety of suboptimal solutions. So we can see here an example of what we have on the left side is the type of variations we've got from training different neural networks with different initializations without pre-training. So the spread over that space is kind of big. So just to say that there is no meaning to X and Y, they are just kind of dimensionality reduction approaches. So it's unitless, but what we can say at least is that they are quite varied in terms of where they are converging. So and likely they are converging to different local optima. And as such, it's not necessarily that good because it may require many of these training may lead to poor performances compared to pre-training, where I would say good pre-training allow to start the neural network in a good configuration, and then it will converge with supervised learning into something that is better. And so that was proposed at first as a way to train deeper neural networks by pre-training them in an unsupervised way to allow them to be usable for some tasks. There were several ways of doing this. One was restricted Boltzmann machine that is no more used. There was also the idea of making use of autoencoders, which is still used, which is an approach that has kind of is continued to be used for other users, but it's kind of it was a way to do this unsupervised pre-training. The idea of autoencoders is to have a model that is capable of compressing the input. So we have, I would say, raw input, which can be something relatively big in high dimensionality, and we will compress that into something of a smaller dimensionality, where we would compress the information that is available from the data into something really, really more compact. And then we will decompress that. We will use a decoder that will go from the compressed representation back to the original representation. And the point is that we want to be able to do this encoding, decoding, this compression, decompression in such a way that we lose as little information as possible. So we want to train such a model to compress while keeping what we call the reconstruction error, which is basically this kind of differences between the original and the X-hat, which is the reconstructed data, using the L2 norm over that. So this is the error criterion that we want to minimize, and as such, we want to keep the X-hat to be as similar as possible to the original X. So we can see here that we have a model of a simple autoencoder with one layer of encoding, one layer of decoding. So we see here like the original data X, which is represented in some dimensions. We have W1, which are the weights of the encoder, basically a linear model here, which compress X into Z. Z is of a smaller dimensionality, but we try to capture the information that is relevant, that is seen in the dataset in X. And then we have the decoder. Often we will use the same weights than the encoder, but transposed. It works that way. And then we want to reconstruct the X, which we call X-hat. And then we want to learn somehow the W1 here that will minimize the reconstruction error that will allow the X-hat to be as similar as possible as X. The autoencoder is trained in an unsupervised way. We don't need any labels. We just need the data, and we try to learn a model that will be able to compress that data in a way that the reconstruction will keep the data as much similar as it was at the input. So the encoder here is somehow extracting a compact representation of that data. And that is done because if we provide it a big training set over some data corresponding to some kind of task or some kind of context where we gather data, I mean, that data set is still somehow sparse versus the input space. You know, we are not covering every possible cases. We are covering the cases that we collected that is probably in a small part of that input space, and the autoencoder should be able to capture that space, should be able to capture all the subtleties that we found in that part of the input. And then for all the areas of the input which is not covered at all by any samples, it should make a really much more, I would say, compressed representation of that, possibly just skip or not capturing what is there, capturing what is in the regions of the input space where we have data. So that's the point of making such an encoder, and able to move from an high dimensionality space to a lower dimensionality space, which is the compressed space. The way it was proposed at first, and can still be used that way, is to make what we call a greedy training, one layer at a time. So the idea is that we start with one layer, so one weight layer to encode, one layer corresponding layer to decode, and we learn that. So we go from like the original space to a compressed space, which may be lightly compressed, depends on the shrink in terms of dimensionality. But we repeat that several times. So we'll add 1, 2, 3, 4, 5 layers. So every time we learn layer 1 says to start with, then we converge to some kind of layer 1 solution, and we freeze that, and then we learn layer 2 over layer 1, and then we learn layer 2 over layer 2, and so on. We need also a nonlinear transfer function between layers, otherwise it will not work well. In fact, because we can simplify many linear layers that are stacked together into a single linear layer, so there's no use for having many linear layers one after the other without having some kind of nonlinear transfer function. As soon as we've got some nonlinear transfer function, that's okay. We know that it is meaningful. In fact, it is the point of neural networks of having many layers like this. And we are learning the weights by gradient descent with backpropagation as we know it. In fact, it is not backpropagated as is for autoencoder because we are training the last layer, so it can be said to be trained. Well, yeah, not exactly. We can see that there is some kind of backpropagation done here because we need to go through the encoder and the decoder and use the reconstruction error as signal to propagate the gradient. So we do some kind of backpropagation to train such a model. So the point is that once we finish the training of the autoencoder with the encoding weights and the corresponding decoding weights, we can just trash the decoder and use directly the encoder as a way to represent efficiently in a compact way the input, and then add a new layer or many layers of classification from the compressed representation obtained with the encoder. And then we will train, says, one layer, one output layer over that. And using, well, we could train it directly on that and keeping the encoder weights frozen. We can also fine-tune the encoder weights. That's another option by fine-tuning them using backpropagation. So of course, the training is mostly done on the output layer, but the backpropagation signal will go through all the layers of the encoder. And the point is to possibly make some adjustment of the representation over the encoded, the compressed representation to make it more efficient in terms of the, I would say, final classification test we are looking for. So an example here of training on a autoencoder says we start with one layer, one linear layer, and we do some unsupervised. We say unsupervised in the sense that we are using the reconstruction error, so there's no label here, but still we are using the squared error of x minus x hat. So the reconstructed x versus the original x. So we are minimizing this error and learning W1 here. And automatically we've got W1 transpose, which is the weights of the decoder. And then we have some kind of representation as said here, which is a compressed representation of the X that should be capturing most of the information. Then we will go to the next step where we will add a second layer for the encoder and as such a second layer for the decoder. So what we see here is that we have the X, it goes through the W1 that has been trained previously, that is fixed frozen for now. And now we have a new representation over which we learn a W2, which will make the mapping from that representation to a new Z representation that is even more compact. And likewise, we need to decode. So now we keep the decoder corresponding to W1 close to the output frozen, and we are using the W2 transpose, which is dealing with directly with the Z values and map them in a way that the rest of the decoder can process it. And we do that like one layer at a time, so we can have like more than two. We can go like it says five layers for encoders, 5 layers for decoders. It's possible. So this is again an unsupervised way training. So basically W2 is trained in an unsupervised way while keeping W1 fixed. And we still look to minimize the reconstruction error x minus x at using nominal 2 of x minus x at. And we have a new intermediate representation here that is representing a possibly even more compact way the x's. And we can repeat that several times to get several layers. Now, when we are done with training the autoencoder, we can keep the decoder part, can be useful in some cases. In some others, we may not need it anymore. We just keep the encoder, which is really making, I would say, a representation learning of the X in a way to compress the information, and that is used as input for a linear layer for classification. For example, it can be several layers. It depends. It's up to the setting that we are figuring out that are good for that. That says that here we have only one linear layer that is making the mapping from the Z space, which is the output of the encoder, to the decision space about, says, 4 classes that we want, in which we want to classify the X data. And then we are learning this W3 in a supervised way this time, using the labels of a sum training set. So we need a training set with the input and the corresponding labels that we will learn to map in that H function. So it is made with backpropagation, and often W1 and W2 will be fine-tuned. So the signal will be used first to learn the weights of W3, but will be also used to fine-tune W2 and W1 to make them particularly fit to generate a representation Z that is useful for classification in our current case.